All right. We should be going here. Once again, welcome everybody. This is the PyTorch workshop. The GitHub repo is, we already had it on the board. There we are. Basically, in this repo we have the things for later, the demos and so forth. And we also have
the slide deck.
The slide deck, and also the instructions for installation and so forth. If you want to follow along with all the demos, you're going to need unfortunately TensorFlow, because we're using TensorBoard. You're going to need PyTorch, of course, and also TensorBoard X, which is the version of TensorBoard designed to work with other frameworks, including PyTorch. So I'll just start out with an introduction of who this workshop is for. You're going to get the most out of this if you know the general ideas of deep learning frameworks, how they work. It should be a ground-up introduction to PyTorch. Basically, we are going to go through some of this basic background, but relatively quickly. So I'll just describe what we're working with here. This is a neural network. This is two ways of visualizing a neural network. A neural network is just you have some vector input, and then you compose a bunch of matrix multiplications and a bunch of nonlinear element-wise functions. So you have your x, which is your input, your weight, then you ReLU function on top of that, another weight, ReLU function on top of that, etc. This, you should all be familiar with this if you're familiar with neural networks. The thing is that in order to build these, we need a lot of very complicated infrastructure. We need to have something which can do all these incredibly large matrix operations, can do them quickly, and will allow us to build sometimes these very complicated linear algebraic operations without too much difficulty. We have a general computation structure. That's how this works. That is what defines the network. And we want it to do the gradient descent for us. We want it to be able to differentiate through the network so that we can actually find the derivative with respect to the weights of the loss function, so that you can actually do the gradient descent that we need. And we need it to be as general as possible. It needs to be very modular, so it's easy to work with, and so forth. We also want very little boilerplate. This is one of the things that deep learning frameworks are most susceptible to. Lots of them have tons of boilerplate because people try to make everything so general. There's a lot of stuff that goes into building and training a neural network. So these are some very, very strong requirements on the sort of a deep learning framework that we need and what's going to make a good deep learning framework. So, I believe this is your slide.
So let's get into something called define by run. So if you guys are familiar with TensorFlow, you'll know that the way that TensorFlow works is, we build out our computation graph, that neural net structure that we saw a couple slides ago. We build that out ahead of time, and we feed our data through it. And then we have to manually put in our weights, put in everything, and it'll update that in what is called a session. That's the way TensorFlow works. PyTorch, on the other hand, is different. PyTorch works by define by run, where we don't have this pre-built graph. We build it up as we do these sort of computations. So we just define, okay, these are the sort of computations we will be doing, but it isn't static. It will be built. We are going to save the weights and do everything on the fly. And so this is good for dynamic inputs, such as variable length sequences. And as you'll see shortly, once we actually start coding, it can make coding a lot easier. All right.
And the next one is objects.
Yeah. And so let's get into a little bit about PyTorch objects. Again, this is something I'll clarify a little bit more once we do a little bit of live coding. But for now, basically, let's look at what a PyTorch variable is. This is sort of the meat of PyTorch objects. It's what you run through when you are training a model. You update it. So inside a variable, you have three things. You have the data. That's fairly obvious. You need that to pass it around. The gradient, called grad here. Again, we'll need that for when we update our model. When we use some sort of optimizer, we'll see again what that looks like shortly. And the creator, that's important because, when we do backpropagation on neural nets, we need to know where we're going to pass our gradients to. So it's important. So that's why we need all three of those things, and that is what goes into a variable. And this isn't quite like a placeholder in TensorFlow, because again, like a placeholder doesn't have any actual value until you put stuff in it. A variable always has its value. Before we go on, does anyone have any questions about anything we've talked about so far? No?
Can you see what the creator is again?
Yes, so the creator is...
I've drawn something back here.
Sure.
So the creator is basically a pointer to the variable that created it, and information about how this variable was created. So in define and then run frameworks, like most frameworks, you define this computation structure. Everything is sort of very general, and then whenever you need to, for example, find the derivative of the loss with respect to this weight, okay, that weight has been placed at this point in this graph, and so we can look through that graph. Because PyTorch is defined by run, it needs to build that graph dynamically. And what that means is, or the way it does it, is that creator variable not only it is a field in the actual same thing that holds the data, and that defines the graph. So if you have, if you have your graph here, and maybe this is a matrix multiply operation here, you are going to be building out this this graph. You can think of it almost like a linked list if you only have one creator per operation. That will be built on the fly. And instead of having this space in the graph to put in data, you have this data object which also has notion of what the graph is itself. That's how creator works.
Yeah. And also another data type that we have in PyTorch is the tensor. So that type you can't, do gradients on and update in that way, but they're still a useful data type to have. You can basically think of them like NumPy arrays, but you can convert them to work with CUDA. For those of you who don't know what that is, it's a framework that allows for parallel programming, which is very useful. We'll see that shortly. And you can convert it to a GPU version, for when you're doing training on a GPU, and it works well with variables. So it's basically just a PyTorch class that works for that.
The data and grad in this autograd.variable are tensors. So that's sort of how variables wrap tensors for use in the actual neural nets, where you need creator to be able to define the structure. You need grad because you're going to have to do gradient descent eventually. And you also, of course, need data because it's holding the data. Mm-hmm. So let's go to the next one. This is a little bit more about how this computation graph is created on the fly instead of beforehand and then run through.
Yeah, so basically here, go back. Yeah. There we go. All right, so here we can see we're going through some calculations. So first we're instantiating a variable where we're taking a random number with Torch's built-in functionality for that, and then we're making another one, and then and that's a random vector with shape 1 by 10. We're making another one with shape 1 by 20. One with shape 20 by 20 and one with shape 20 by 10, and we're doing some matrix multiplies here and the addition, and you can sort of see in this graph how we come to do that. So we start with our variables w sub h, w sub x, we do matrix multiplies, we get some partial results, we add those up, and then we get our output. Unfortunately, the GIF or GIF couldn't quite render here properly, but basically, if it had, you'd have seen that the top layer would have been created first, and then the next layer with the 2 matrix multiplies, then the third layer and the fourth layer, and so on, and it's created as these operations are, so that shows a little bit, just a simple example of what we mean when we say a dynamic computation graph.
This is created basically top down as you see it here. And whenever you have a particular node in the graph which is connected to the previous ones, those arrows, the edges are pointed to what was used to create it. So that's how you actually look at, that's how PyTorch remembers where everything came from, so it can actually do backpropagation through arbitrary structure.
Mm-hmm. Does anyone have any questions about that?
Transpose.
Yeah, that's how.
I don't know why they didn't define it with the transpose to begin with.
But yeah, that's just how you do transpose. You can do it that way, kind of like in NumPy. Okay. All right, time for some live coding.
I did this wrong.
All right, you want to open up the notebook there?
Yeah. So there's something weird here. We are doing a screen capture. And the screen capture is capturing this screen, which is distinct from that one. So what I'm going to be doing is escaping both of these, and then basically dragging over the notebook as I use it, and it's also going to be I'm also going to have to drag it back here every once in a while. So that it'll show up on the screen capture. This should all be fine.
Question.
Yes.
Are you not able to mirror the display from your computer onto the projector for this entire screen?
Perhaps, but we haven't. Let's see. All right.
Do it now, or like just kind of do it on the spot.
I don't know how. All I did was plug in an HDMI cable.
You can probably look it up in the settings. Eventually.
In any case,
Before you just
we're gonna do this for now. It shouldn't be that bad. So. And especially if people are watching this later via the screen capture, they can have with significant ease the actual notebooks in front of them as well. So it's better to just put that up there for now and worry about it later.
So, random question.
Mm-hmm.
I'm not familiar with PyTorch, so I don't know what does that mean?
Unfortunately,
Yes.
yeah, a little bit anyway. The you can follow along without doing it yourself. You can always get a virtual machine or a dual boot or something like that, but it does use those are the only ones that the PyTorch website itself supports. You could look up to see if someone has managed to put it on Windows. I don't know if they have.
Yeah, we'll be getting to that a bit shortly, but anyway, now let's go back to this Python notebook here. So PyTorch MNIST skeleton, if you could all put that up. So let's just step through this notebook sequentially for a second here. So first, we just have some standard imports, torch.nn, and then functional. Why can't I scroll down on this? Oh, there we go. There we go. All right. So we have the variable class. We have some dataset classes that we'll be using later when we load and pre-process our data. An optim, which is for the optimizer, we'll be using stochastic gradient descent for this. And that about covers that. Now let's start coding this up. So you see here that we have a number of different arguments that we want to fill in with different things that will help us run. So we have the batch size, test batch size, epochs, learning rate, momentum, CUDA, log interval, and seed. So epochs, how many epochs of the data we run it for, where one epoch is a whole pass through the data, our learning rate, how much we adjust when we update with our gradients, momentum, that's something that helps us go ahead in the direction that we've already been updating our gradient, helps us converge faster usually. CUDA, again, as I described, a framework for parallel program that has PyTorch support, so is helpful in speeding stuff up. Log interval, we're going to be using that for one to actually log output results, and seed is something we're going to be using for pseudo random number.
Just start filling these in.
Yeah.
As you talk.
Pseudo random number generation. Just this isn't so useful now, but it's just something to remind you of good practice that you should use a seed for reproducible results, because that's always a good thing. So.
Epochs, we're not going to be able to run it for a lot.
Yeah.
Because we're going to have to move on to the rest of the slides. But
the parameters.
we have parameters that we've set up in a different notebook, so I'll use those.
Mm-hmm.
We yeah. Oops. Is this good? Let's see. There we go. Is this better?
Oh yeah.
Awesome. So we're filling these in with the values that we used. It doesn't much. You can choose whatever values you like. CUDA is just going to be whether or not we're using CUDA.
Mm-hmm.
So let's use CUDA for this one.
Oh, and so also we have another notebook in the repo, which is the solution where we filled in all the things that we've left out here, just in case you want to look at that later. For now, we recommend you look at us live coding it, because we're actually going to be explaining things. But yeah, if you want to look at it on your own time later, we also have that in the repo. So. And at the bottom there, you see we have this other function, torch.cuda is available, because we want to make sure that we don't get errors where we try using CUDA, but the machine we use doesn't support it. So, again, useful flag for when you're doing stuff with CUDA and you don't want it to error when you don't have it. So yeah, once you're done there, could you maybe raise your hand or something so we have some sort of indication of when we're okay to move on? All right. Yeah, and don't and everyone just take your time if you want to ask some questions or just play around with it a little bit. Don't be pressured at all. We just want to know. So. All right.
Any questions on this? We're going to be going pretty slow through this so that everybody can follow along. And if you hit some error that we don't hit, we can have time to figure it out. Anybody hit such an error? Yeah.
Well, that's just, for the test batch size, we're going to be validating our model on test data. So we just made that a separate parameter, and batch size is what we're going to be using when we're training our model.
Test batch size doesn't make as much of a difference.
Yep.
Batch size, since it's what we're using when we're training, it affects how noisy our gradients are, everything like that. Test batch size, that's just how many we do at a time when we're going through the testing data. Say again?
Why is it so big if there's one?
That's just, well, there isn't really a good reason behind that. It's just what I happen to train on, but it's not, again, it doesn't make too much of a difference. We're just keeping these values because that's what's in the solution repo. So, if you're looking at the solutions and watching this later or something, consistency, but don't worry too much about that. All right.
So we're going to go on to the next one. Is there a way to turn this on? I think this is what this is, right?
Yeah. All right. So yeah.
What was the log interval?
So that's what we're going to be. That's a number to determine when we actually output stuff as we're training. So after a certain number of iterations, so we call that log interval there.
This is all filled in. This is just getting the actual MNIST data that we'll be using
and normalizing it and stuff. So,
we have all that code filled in. We don't have anything for you to fill in there. This is unfortunately one of the. I don't know what's causing that. This is unfortunately one of the areas of PyTorch where there is boilerplate. It's just the data loading. That's basically unavoidable because data loading is always tricky. Thank you, Brenton. I don't know what's causing it either.
Keep on going.
All right. We can just run this, and it'll download our data for us.
Yeah.
Because I already have the data downloaded, I think it's just worked for me. Yours may say what this said to begin with.
Which is just like downloading, like it'll have some link from like Jan LeCun or whatever, because he was one of the people behind the MNIST data set. It'll say that like 3 or 4 times. Might take like a minute or two. So yeah, since this may be your first time downloading it, just be like a little patient, and then it'll work. So yeah, now
you can just read through the description here. This is just a description of what kind of a thing we're doing. Basically, in here, we're going to actually be creating the net itself.
Sorry, before that, can you say a bit about why the normalized constants are these
Oh, again, I just sort of took this from another repo that had those normalization constants. I mean, this is MNIST data, so it's not that hard to train a model to do well on it. So at least in this particular case, I wouldn't worry too much about like what the constants are, and more just how the data normalization is done, right? Yeah. Okay. So yeah, if no one has any more questions, then let's move on to actually coding up this model. So now we're actually going to build a neural network in PyTorch. So let us do that.
Do you want to do this with sequential?
I'm going to be doing it this way.
This way, okay.
Yeah, no.
As you write that, I'll explain.
Sure.
So basically, the way we write our code in PyTorch is that we create everything in classes which extend nn.module. nn.module is a general class for having some neural network module. Basically, what we're going to be doing here...
Wait, hold on. Can we switch maybe? Because I'm not used to coding on your computer.
All right.
So, yeah. So, like Nate was saying, everything we do is inherited from this nn.module class. It has a lot of things needed for training and for training a model. So all the nn.module nets that we make will have an init, and what we're going to do, the first thing we're going to do is we're going to call the superclasses init method, which in this case is nn.module.
I'm wondering if I should be doing this with sequential. It seems like it would be a lot easier. Make a lot more sense.
The reason I'm doing it later is because when we actually play around with the weights, and I can like pull out individual things.
Okay.
Yeah. Yes. So you'll see later why we're going to be doing this in a slightly elongated way, which is a bit clunkier than what we would normally do when making something, but it'll prove useful later when we get to how you can like interactively play with things in a way that you can't with TensorFlow, thanks to like the dynamicness of it all. So we are going to start with a convolutional layer here, like we say. So this one has an input size of 1 input channel, an output size of 10 input channels, and a kernel size of 5. So you can think about it when we are convolving something with a filter. Those are the specs of said filter. And then we're going to be doing max pool 2D with a kernel size of 2. And then we are going to be doing an activation, which in this case will be ReLU. And one thing that you'll notice as we write this stuff out is that we aren't actually taking in the actual argument of anything that we're passing through, because again, this is dynamic, we're just initializing it here. You will see in the forward method how we actually run it with some input data. So here you can see we have this pattern, conv, max pool, ReLU, conv, max pool, ReLU, and then in between, we're going to be having some dropout. We're going to have two-dimensional dropout because that is the shape that our data is. So does anyone have any questions about this code as we're writing it? Yes?
Can you explain the parameters for the comp like the 1, 10?
Yeah, so that's like the number of input channels that we have for our image, because in this case we have one input. We want it to have one input channel, then we project to 10 output channels, and we have a square kernel of size 5. Does that answer your question?
Yeah.
Cool. Anyone else have any? Yeah? So basically what it does is when you have the result of a convolution, you want to like combine information spatially into some sort of summary statistic. That's often useful because suppose that we have some sort of rotations of images. Sometimes you might have certain rotations that capture information and others that don't. So you can consolidate it and then look at where the information is invariant of rotation. Does that make sense?
How does Maxpool like do what you just said?
So basically what it does is suppose that can you see this?
Yeah.
So this is a highly simplified version, but hopefully it should express the point. So let's say that I have this 2x2 thing, and then I have this is like one region of my image, and let's say that I have these numbers as the output of my convolution. Since it's the max pool, it'll take the max across this region, which is 10. There's other sorts of pooling, like average pooling or whatnot, but max pool tends to work the best because, again, it's like looking where the information is. So, you know, when you do a convolution, it'll be the highest when our filter picks up something. So then max pooling allows us to, again, be invariant of where it is so we don't get fooled by rotations as much. Does that make sense?
Yeah.
All right, so let's see where we are with this code. So mostly unchanged. So then after self.activation FC, which is another ReLU, then we have so we have two linear layers, one of size 320, which projects down to 50. We have an
For the dropout layer, do we not need to pass in the dropout probability?
It's a default.
Currently, we're using the default dropout probability. That is where you would pass in the dropout probability if you were using something else.
All right, he preempted one of my questions. So what is the default dropout probability?
0.5.
Okay, that makes sense. The other question, what's the default padding, valid or same?
So it actually doesn't work that way. So instead what you do is
some of the things do.
Well,
Go
so what
ahead.
you do with convolutions is you specify your stride and your dilation factors, which you can use to then manually do that. It has a default stride of 1 and a default dilation of 0.
Okay.
But it's not like TensorFlow where you explicitly pass in same or whatnot. You kind of have to do a bit of calculation to get exactly what you want.
Okay.
I believe you can pass in same in some cases, but it does allow you to fine-tune those and has more native support for fine-tuning those a little bit more.
Mm-hmm.
Okay, so the default is valid padding, i.e. no padding.
Yeah.
Okay.
Yes.
Does the convolution layer and the top pooling, do they only allow square kernel sizes, or can you actually just continue like insert like some other like secondary for like 2D? Can you make it like 5 by 3, etc.?
I think I'm pretty sure it only allows square kernels. You could probably do some hacky thing to get a non.
I'm actually not sure about this. It may allow non-square kernels. If I recall correctly, you would have the kernel size be something like this instead.
Oh wait, no, yeah, sorry, you can do that. You can. What you do is, you just pass a tuple or tuple instead. But yeah, if you only pass in one value, then it just assumes that it's square. Any other questions? Yeah.
What is dropout?
So dropout is basically a way of regularizing neural nets. So what you do is when you take some input, you selectively decide not to pass it forward with some probability, which is our dropout probability, which, as was discussed earlier, has a default of 0.5. And the reason that we do this is it forces other layers to learn what was dropped out, so it provides like more regularization and more generalization. Does that make sense? Yeah. Cool.
We should explain the structure of the nn.module class and the structure that you'll actually be writing things in when you subclass it in order to make your own model. Do you want to copy this over for now while I explain?
Wait, hold on. Let's do it the other.
All right. You can go ahead then. So I'm just going to explain why we have to write self dot for all of these things because register. Yeah, go ahead.
So basically, the way we're doing it is, there's two methods. We have the init and the forward. So the init defines all of these structures that we're going to have in our model. So, we have a model of that structure, and then in the forward method, we actually pass in data and run it through the model. So you can see here we have x is equal to self.conv1x, so that means that we're actually doing the convolution. Sorry?
Oh, yeah. Thank you. I'll do that. Don't worry.
Was that everyone's thing, or is there any? Okay, cool. So as I was saying, you do your convolution, then you do your pool activation and so on, we'll be breaking it up. So there's a couple different ways that you can actually do this. The reason I chose to do it this way is shortly later in this notebook, we're going to actually have we're going to actually play around a little bit with the model. There are other ways of doing it, such as doing it sequentially, where we essentially make like certain parts of our model and compress them into one. So for example, if you were to like go up here, you see like say self.conv2, conv2 drop pool2, whatnot, we can wrap it around something called nn.sequential, and we can just call that something. So let's say we could just call that self.part2 of model, and then like we can just run our data through that way, much like we are doing here. But then, you can't play around with the individual stuff as much, so I made it more explicit for now, but there is a sequential API which allows for that. And you can see here that what we have to, we have to like change the dimensionality of our data in order to have all the dimensions work out. So, we're going to be doing that down here. And so we have our init, and then we have our forward, but what we don't actually have is a backward, and the reason for that is with PyTorch we have auto differentiation, where so long as we define our forward, then recall earlier when we had PyTorch variables, it had the gradient and the creator in it. So armed with those things, it can do the backward automatically for us, so we don't actually have to go out and write backprop ourselves. We can just write out the forward, and it'll know what we want. Does that make sense to everyone? Do you have a...
No, can I skip that?
No. This stuff?
Question, the x.view, is that kind of like reshaping?
Yeah.
That is reshaping.
That's exactly what it is.
Mm-hmm.
Yeah, that was my question.
We have a lot of similar questions here today.
There are a number of ways to do reshaping in PyTorch. This is the one you'll see most commonly, and I think they all basically reduce to this. -1 allows it to infer that size, so you can't put -1 in multiple places. But since we're going to be doing this with batch sizes, and we want it to work generally for any kind of a batch size, the first index in any tensor is always the batch size, if it's a data tensor that's going through the network. And so it's going to infer that first one based on what the actual number of floats that it has in that tensor is. So that will allow it to reshape it to 320 dimensional, but still maintain the batch size nicely.
Oh, actually, one thing that I want to quickly mention before we move on. So kind of like how, you in the white jacket asked about whether or not you could do non-square kernel sizes. You could also do... So I mentioned earlier about like stride and dilation, how you can like change those to like change your padding and whatnot. You could also do those in non-square increments as well through the same sort of tuple passing. Just something I kind of wanted to make clear to you guys. So yeah, a lot of things that you can do in non-square ways so long as you provide the tuple/tuple that you would use. So before we move on, does anyone have any questions about the basic net model that we wrote? Yeah, White Jacket.
I'm actually kind of confused as to where you're getting the 20 from. Is it like, I'm not entirely sure like how you reshape the output of the second convolution layer for it to have 320.
So this is something that you just have to deal with whenever you're building a convolutional network. Is the general structure is usually you have these convolutions and poolings, all of these operations which take in two-dimensional things, and eventually you have to reshape it to one-dimensional so that you can use linear layers. Once you shape it to that, it's not really the case that you can have that size be generic. You can't make that size general because you have to know what is the actual size of your weights going to be. 320 is based on what the conv and pool is the actual number of floats that are going to be left after we've removed a lot of dimensionality from the data, but through these pooling layers and also the convolutions. If we did convolutions a little bit differently, it would be different. If we did a different padding for the convolutions, or if we did a different kernel size for the convolutions, or a different kernel size for the pooling, then that number 320 would change. For the thing we've built up here, it is 320. So we can just run this cell and get on to the next one because this is all the code that you need in order to define a model.
All right, so now we've defined our model, but now we actually need to train it to run. So the way that we're going to be doing that is, so first we're going to define an instance of our model. So
net, as you recall, was the name of the actual class that we put all our code in. And so whenever you need to create a new instance of whatever model structure you've just defined, you just create a new instance of that class. And it creates new random parameters, randomly initialized parameters, new instances of all these operations, etc.
So yeah, and then as you can see over here, so if CUDA, you convert the model to a CUDA model, and now we're filling in the code for our optimizer. So as I said before, we're using a stochastic gradient descent optimizer, and it takes in a few different things. It takes in the model parameters, so each model has its own dot parameters, so that are the different weights. And again, because we defined this model as a subclass of the NN.dot module, it knows how to keep track of its parameters, so you can just trust that works. So those will be like all the different weights we have for like our convolutions and linear layers. Recall that we defined our learning rate and momentum earlier above, and so we're going to be using those here. Does anyone have any questions about this? All right, let's run this. What? Okay. Did yeah. I guess. Yeah. Did I shift something or?
What was the? At what point did we run the above? Did we run them all in the correct order?
Yeah, let me just go through and run them again. So.
All right. While we figure this out, let's see what it is. Before module.init. So there was one thing that we forgot up here. Because it is a subclass. Because it is a subclass of module, we needed to. Is that in the solutions here?
Yeah, it is.
Okay, that was just my bad. I didn't copy it over. That makes sense.
So I guess like back to like connecting it with what is a PyTorch object.
Mm-hmm.
So like which like is it the next class? Like what's the PyTorch object in this example?
So we have this model which inherits from the module class, and within that module class, we have different things. Like we have our convolutions and whatnot, and those have certain weight parameters, and those are parameter classes, which are instance of variable classes. And within those variable classes, we have the gradient tensors and everything that we described earlier. Does that make sense?
So it's kind of like inherited from
Yeah.
NN.module.
Mm-hmm. Exactly.
Could you scroll back to the that superclass in it, please?
Yeah.
This is just a standard superclass init that you would use for basically most subclassing you do in Python, because it uses this sort of superclass structure. It has to do this, and there is some fairly complicated code in the nn.module class itself, which has to run before it can be able to register all the parameters when we say self.conv1 equals nn.conv2d, etc. Yeah.
Mm-hmm. All right. We good to continue?
Mm-hmm.
All right.
I should note, just for the benefit of the screen capture, that we haven't really been moving this back and forth, and I don't think that's a good idea to move it back and forth. But everything that we're writing here is verbatim from from the solutions notebook, and we're just writing it ourselves so that it's easier to talk about line by line.
All right. So here we have some standard code to train the model. So we're looping over all of our batches. Model.train is something that we do for dropout because we want to make sure that we apply it at train time. So we turn on dropout that way. We loop over our batches and we convert our data and labels to CUDA if we have it. That's something that needs to be done. We set our optimizer to 0 grad so we don't accumulate gradients across runs. We feed the model our data, and then we calculate this loss from the output and target. We backpropagate the loss, and then we do an optimizer step where we actually update the weights. And then, if batch IDX and log interval, so again, log interval just tells us when we print stuff out, we print stuff out. Fairly straightforward boilerplate.
I want to note a couple of things here, which are quirks of PyTorch, quirks of the syntax that we see here, and also good things about the syntax that we see here and why it's so general. Firstly, there are two different .CUDA methods. One that works on modules and one that works on like tensors and variables. And they behave differently. The module.CUDA method will take whatever your module is. Your module holds a bunch of parameters and everything, and it'll convert all of the parameters that it holds to CUDA one by one and just keep them there. And so now your net, or whatever module you have, has been converted to CUDA. All of its internal data is on your GPU. For tensor, or autograd.variable, .CUDA actually returns a new tensor or variable, which is on the GPU. So if we were to, we're not going to do it for fear of messing some things up, but if we were to just print out data, right, or target, before and then after we set it to the new one with .CUDA, one of them would just give you all the numbers, and one of them would give you all the numbers, and below it would say, on GPU 0. That's something that should be noted here. The other thing is that you can see there's a lot of what looks like useless boilerplate, right? Why do we want to zero out the gradients all the time? What's the loss function? Why do we have to say loss.backward and optimizer.step separately? This is part of why. This is part of the consequences of PyTorch being very general. You'd think, of course, we want to zero out the accumulated gradients every time, but in fact, we don't always. We have been actually working on a project where we have to do a lot of weird things with LSTMs, with batch sizes that don't match up, or sequence lengths that don't match up within the batch, and it would be really weird to sort of permute everything in order so that it would actually work and we could feed it through in batches. This is a way to do batching without actually using batches, because you can just not call optimizer.0grad in between all of your calls, and it'll work exactly the same. I also want to note about the loss here. The way it works, if you'll note in other networks, in define and then run networks, or in frameworks rather, you probably couldn't do this. It makes a lot of sense to have the model somewhere else and to have the loss function in the training code, because the loss function is fundamentally a notion of how you train it. It makes a lot more sense to have it here. But in define and then run networks, frameworks rather, you really couldn't do this, because it expects everything to be put into the same graph so that it can run it in its optimization, in its optimized way. It makes a lot more sense, some of the things that you're able to do with PyTorch, because it's defined by run and it doesn't care where you put everything.
Yep. So let's step through now. So testing the model. This is test code, which works basically the same way as the training code. The only difference here is that since we're running inference, we're actually going to be making a prediction about which of the digits it is. So we convert from a prediction vector that we had when training to an actual number, and we have some code to calculate our average loss, but other than that, it's the same. So
again, a couple of notes here about where all of the parameters are actually used. We define batch size and test batch size up at the top of the notebook, and we don't see them in here. Those were actually used in test loader and train loader, and this is basically just to give you an idea of where PyTorch likes to put its various parameters and everything. This test loader class is something that will give you batches automatically as soon as you call next. And because of that, it sort of nicely abstracts away all of the transformation and the batching and everything like that. There are other ways of getting data and running it on a network in PyTorch. We could use the test set directly if we wanted to just iterate through that. Here we've used the test loader, and it abstracts away a lot of that difficulty for us.
All right. Anyone have any questions about that? All right. Let's step through here. So now you can see. So yeah, much like you guys, now this thing is learning. So yeah, here we can see we've got our loss going down, and I hope. Yeah. So.
So we can see our losses decreasing. We'll see later in some of the more complicated examples how we can use TensorBoard to actually see the graph of the loss.
Yeah.
But
for now, we're just going to stick with good old printing.
I'll scroll down to the bottom pretty quickly.
Yeah, so we're just cycling through different epochs. Nothing too exciting here, right?
As this is running, and I think it's basically finished running now, any questions?
What's data in target?
So that is the actual data that we're feeding in, and then targets are the different labels.
What is that like?
The input and expected output of the network. So if you look at the code that it runs there, it will say something like, after doing all the transformations on data, output equals net of data, and that will run the net that we've previously instantiated on that data variable, and then it'll go into the loss function and use the loss function to compare it to target. So that's how it basically does this. This loss function, how it sets up all the variables. The data and target are just our names for it.
Question?
Is there any way to not print the knowledge of stuff?
Yeah, sure.
This is just why the way we've set it up here. And you recall we did log interval, which was just after how many batches we would print something out. So if you made that lower, it wouldn't print out as much.
Yeah.
The printing isn't a function of PyTorch. It's just the way we've written this notebook. PyTorch doesn't print anything at all if you don't ask it to.
Yeah, white jacket.
Brenton, what is it?
Is it required that you have like all the data loaded in this data loader and use the data loader to run this? Or
You
can you just manually
No, yeah, you can manually do it because again, if you look at how the net is defined, it's very easy to pass in data. So long as we've converted it to PyTorch variables, you can do it manually. But it's like we use a data loader to show good practice. It helps. It can massively parallelize things and whatnot. So it's good to use, but not required. Any other questions? Yeah.
So how is this different than
Keras?
We will show the differences between some of the more striking differences between this and define and then run frameworks later when we do the dynamic graph and a number of things that you couldn't do even in high-level things built on top of other networks like Keras is. A lot of the code that you will end up writing is very similar, but occasionally there will be something that you want to do differently. Occasionally there will be something that you absolutely just can't do in Keras. And so we'll see later when that occurs.
All right. So if there are no more questions now, I'm going to move on to kind of playing around a little bit with model attributes. So recall that we define model as an instantiation of our net class. So here if we print out model.conv1, you see that we can actually get the metadata on the convolutional layer itself because, again, unlike TensorFlow or other things where convolutions are strictly functions, this one is an object which keeps track of its own data. So you can actually modify it and change it on the spot. So you could say something like model.conv1.kernel size is equal to 3, and you can just change it that way. And then when you run the model again, it'll just change to something else. And then if you print out the weight, this is a parameter, which recall earlier is what we take all the parameters from our model and feed them in for when we're doing our optimizer update. So this is just a big giant vector thing. Don't worry too much about the actual values, but this is just to show you that the parameter class is a thing, and that is where we actually store the weight. So much like I was playing around with the kernel size earlier, you could play around the weight. You could play around with anything interactively since it is dynamically created.
There are a few restrictions on it because it does want to keep the graph structure. It wants to remember what all the gradients are. Mm-hmm. And so if you change something in the middle of training, it might complain at you. But in general, it is very, very easy to look at all these things dynamically. I will point out one thing, which is these 5x5 matrices that you see that make up this tensor, those are the actual filters, the actual convolutional filters that we know about, that we're familiar with in convolutions. Mm-hmm. So it's very, very easy to get at those for visualization and things like that.
Wait, so when you do change the weights, what change the size of the kernel? What happens to the weights? For example, when you change from 5 to 3, you're pretty much cutting off what is it, 16?
Well, yes. Well, if you do that, then stuff might break. Again, I'm not saying this as something you should do. I'm saying it's something you can do. So it's up to you to not shoot yourself in the foot with this.
That's one of the guiding forces of PyTorch in general. Is it's up to you to not shoot yourself in the foot. Yeah. Because it'll allow you to do a lot of weird stuff.
Yeah.
Most of the time, if you're building normal neural networks and you just want to build them quickly and analyze them quickly, then you're going to be using things that don't have any chance of running you into trouble with PyTorch.
Yeah.
But I don't actually know if setting kernel size to 3 is something that you could easily do and then run again.
All right, you want to stop for 5 minutes here? Or?
Yeah. So we're at the end of the MNIST sort of demo. Mm-hmm. If we have seen up here, so we trained it. We could also we can just test, and it'll print out. Yeah. Let's see what the accuracy actually was. This should work, shouldn't it?
Yeah.
There we go. 99% accuracy.
Mm-hmm.
And that was very quick. PyTorch is, I should note this is not super great accuracy for MNIST. People have gotten up to crazy accuracies for MNIST. But, there's a myth that PyTorch is especially slow. It's a little bit slower than some of the other networks because it is defined by run. It does have to do these things on the fly. But you can see this is a laptop, simple network, took a minute to train to 99% accuracy.
Yeah.
So it's not horrendously slow or anything like that. At this point, we're at the end of just the first demo. We have a few more slides after this, and then some more interesting demos. But we're going to take a break right now. Just a few minutes, 5-10 minutes.
Yeah.
So if you guys want to get up, get water or anything like that, come ask us questions.
Yeah, if you want to go on Facebook, drop a like at Machine Learning at Berkeley. I'd like that.
Should we also put up the sign-in link?
Sure. Let's link to that.
Do we have that? Anyway, break. We're going to write a link on the board that will be relevant in a bit.
White Jacket, come here.
So for the target is actually actually the Wi-Fi.
I don't want to show favoritism.
You want me to make a sign up now?
What?
Target is actually
White Jacket.
White Jacket. It's clearly gray.
So it's a cream. It's a cream jacket.
All right, good to know for the second half.
Oh, so the data is the X. Just think of it as X value. The target is the predicted Y value. So after running through the neural network, so you get the predicted value, and you have the target is the actual Y value. So what? Yeah, so the output is the predicted Y value. So you compare the predicted Y value and the actual. So you want the predicted to be as close to the actual, and then you compare the difference.
Oh, that's interesting.
So I mean, there's no difference. Yeah.
So what are they data?
What is that? Yeah, there is the X1, the what you start with.
Apparently, it exists. Who did this?
No, it is not.
That sounds like he's just like
Apparently, someone already made it. I think very similar to something like that.
Yeah, this is not linear.
This is like a neural network. I sounded like
They're the same.
I know he's not.
Okay, alright.
They're the same thing that there's an X value you run through it, predicted value Y value. Compare them. Alright. You use that to update your rates. That's machine.
No, I never mind. I thought you were talking about
No. It's
Make this.
It is X value.
We want to call it slash PyTorch.
Yeah.
PyTorch. During the break, we should try to fix this. I have no idea what's going on. Is it this that's making the noise? No, it isn't. What's making the noise?
I don't know what it is. What can I erase? Can I erase the object?
Yeah, sure.
Yeah,
That's a bad eraser. No, this is a better one. That's also a better one.
They're all kind of
Yeah.
It's like a chocolate eraser or something.
So what are the tensors, I guess, in this example?
The tensor is basically just the analog of NumPy arrays.
Mm-hmm.
It's you can think of it almost as like wrapping a NumPy array, except being either on GPU or on CPU.
But I guess were you asking about what?
Well, I mean, how is it applied?
So
here,
yeah, basically,
right?
So basically, what it is like. So remember earlier when we were going over the variable and it has like a data and a gradient?
Mm-hmm.
Those are stored as tensors within the variable class. So it's like tensors with special wrapping around it so that you can like actually use them for updating gradients, right? Does that make sense?
So if you can go for the attendance, tinyurl.com.
So I'm just trying to see how it applies within this example.
PyTorch,
Like,
Sp18.
what's a tensor? I
So-
understand it's like a wrapper for the.
Yeah. So
computer,
again,
right?
let's think about this on the highest level. So let's say that we have our convolution function, right?
Yeah.
Or our convolution class.
Are you just asking like what a tensor is abstractly?
No, like how? Yeah, well,
So-
like what does it apply?
So yeah, again, like
Your input, right? It's
Okay.
going to be in the normal case. It's a vector of numbers. In this case, it would be actually a matrix of numbers, right?
Okay, so
But in this case, since we're doing batching, it's actually 4 dimensions. There's an extra dimension in there for channels, but there's only one channel.
So
right?
it's essentially your data.
Yeah.
Okay.
Or-
Or like your feature data, like training
Yes.
data.
Yes. Or the weights of the network,
Okay.
or the output of the network.
Okay. So it's all
Every type of thing to hold numbers that it goes through.
yeah, it's all
is-
built
is
on
that.
top of tensors.
We're going to need to do some heavy editing of this.
What is automatic differentiation?
Okay, it's not
So
this,
again, that's
I don't
basically
think.
like, remember how when we made our net, we had the init and we had the forward, but we didn't actually have a backward, right?
Yeah, that one is automatically done.
Yeah, because like again, given the gradient and the creator that are stored within the variable, it's able to do it for us. So we don't actually have to write it out.
It's automatically done based
I don't know if it's like a microphone
Yeah.
picking up something or like some connection like being bumped all the time. But I unplugged the microphone from the receiver, so I don't know. That's the best I could do.
Hopefully, it's not too bothersome.
All right, everyone, we'll be starting again in like a minute. So if you could like start to get settled, and yeah, we have this attendance form. If you want to fill it out, give some feedback. That's always appreciated because you know that's how we update our gradients for this workshop.
Oh.
So
Data and target. I guess we do a Keras.
So actually, the Intro to Deep Learning workshop that we run multiple times throughout the semester is done in Keras. So yeah, come through to that. That'll be at different points. Just like check whenever.
Next Tuesday or Monday, can't remember.
It's next Tuesday next week.
All right, there we go. Next Tuesday, you're on top of it. I like it. I like it.
I can't go to this.
All right.
All right, I guess we'll start back up again. So again, this is the attendance and feedback form. Please do fill that out. It's very helpful. I'm going to close this out for now. See if I can bring the slides back up, and we'll get back into it. Here's one of them. Here's the other one.
I got a weird question while you're starting up. So I got a training result that is significantly less good than yours, like 95%. Did I just pick the wrong random number seed? Or did I just screw
Maybe
it?
what could have happened is you were so. Could have been the wrong seed. Maybe or it could have just been like. Wait, did you use our parameters?
Yeah.
Okay. Maybe it could be that you don't have CUDA on your machine, so maybe it wasn't able to train as efficiently, or it could have just been like, I guess, like slight percentage accuracy.
You know, these things are susceptible to random initializations.
Mm-hmm.
If you run it again, maybe it'll be better.
Yeah.
I don't know that I can think of anything off the top of my head that would be something that you changed that made it worse a little bit. I couldn't really tell you.
Mm-hmm.
So now let's start back up again, and let's talk about why PyTorch is so great. Basically, we went through all of this, but the main thing that to keep in mind in terms of what this means for how you actually write code in this framework is that define by run makes everything very Pythonic. If in most deep learning frameworks, if you want to run some computation, you have to define what the computation is beforehand. Then you have to fill that, start some session, and then when you're starting that session, bind the entry points of that session to whatever data you want to do the computation on, and then it'll run that computation and you can get it out of the session. It may not be always that complicated, but whenever you're doing something like that, defining a structure beforehand, using code that runs and defines that, and then using it later to do something where you could have just done that computation directly if you didn't need to do this, define the structure beforehand, you're going to write very weird code that breaks a lot of Python sort of conventions. PyTorch is always very Pythonic. That's one of the greatest things about it. And so if you, there's never going to be a point where you surprisingly can't use a list comprehension here. There's some feature of the language that you really like that just doesn't work for these purposes. Because when you're running things, it's Python first. You're not creating some new program that then runs in the background. What you run is actually doing the thing.
So to kind of give an example of that, one thing I've used that's helped me when debugging neural nets is PDB. It's a Python debugger that allows you to go in and step through things, and that's harder to use in something like TensorFlow, where because it's all wrapped around in a session, you can't natively access things that way, and you can't have interactive sessions as nicely. Where as I was showing you before, you were printing out weights and things. The example that I showed you before maybe was just slightly pointless, but there are real cases where you'd want to print out these things to help you. It's a lot easier to do it in this sort of environment because it's so Pythonic.
The other things here are that it makes a lot of sense to have a forward and backward for each module, and when you actually run the things and your modules all get connected up, right, then everything will work fine. And everything makes a lot of sense in terms of what forward does, what backward does, etc. And backward, which actually computes the gradients, will work just fine. It's heavily NumPy inspired, so if you have, if you're coming from just a NumPy background, it wouldn't make any sense to do everything in a session. That's not how NumPy works. That's not really how Python works even. But PyTorch likes to call itself NumPy, but on GPUs. And so it really does, these things make sense if you're coming from a NumPy background. So we wrote a lot of this code for the MNIST example, but there are people switch from, or in the past, switched from TensorFlow to Keras for the sequential class alone, and that's something that works well in PyTorch as well. There's a sequential class. We could have done the entire thing with just 2 sequential classes and then the flattening in between them, because if you can just put all the operations in a row, and as long as they're actual operations and everything calls the output of the next thing in a nice way, sequential will work just fine. There are a number of things that are like that, module list, things like that. But it does make some effort to cut down on boilerplate where possible. We're going to go through, this is not something we're going to spend a lot of time on, but this is, we're going to, just for comparison, show you the nice way of writing code in TensorFlow for doing the same thing. And you'll see that it's a lot more code. There is also documentation up there, which we didn't have, but it's code that's harder to read. It's you often define these all of the parameters yourself, everything like that. If you don't already know a lot of TensorFlow and its syntax and its quirks, it's going to be hard to interpret. I don't know. Do you want to go through this in any detail, or should we just?
I mean, yeah, not really. Basically, it's like, yeah, I guess also just another thing to add here is that in order to use TensorBoard, you have to like define scopes for things because again, the convolutions are just functions. They aren't first-class objects that remember their own data. So you have to actually give it a scope to say, okay, this is the convolution we apply here versus there versus wherever. So, again, that just adds more to the code, and as we'll see when we do our TensorBoard example, you don't have that. So, yeah, just one more thing to emphasize.
This is another thing for TensorFlow that, just this for computing the loss and this training. And we'll note here that it sort of wraps everything in the optimizer itself. If you wanted to do something more complicated, if you wanted to write your own loss function, if you wanted to not zero out the gradients between every batch, you would have to write C in many cases. Mm-hmm. You never have to write C in PyTorch. You can write everything, even if you're defining your own thing and your own backward function for it. Your own loss function, everything can be written in Python. Mm-hmm. Even if you're including operations from entirely different frameworks. We'll see, or we may see somewhere in here that you can actually use the convolution operator from SciPy, and it'll work just fine.
Yeah.
So let's see what we have after this. There's a couple of good things. We already did the installation, of course, but a couple of things that are good about the installation. I'm just basically telling you why PyTorch is great at this point. But unfortunately, it isn't available on Windows.
Yeah, I think we saw. I'm sorry too.
That's the big drawback. But whenever I accidentally boot into Windows on that machine, I am annoyed, and it's not just because of PyTorch. So. The idea is, since everything is handled with Conda, you rarely, if ever, have to build it from source unless you want some new feature that was just implemented on the GitHub. And you don't have to compile the different versions or anything like that. You're never going to get some TensorFlow-like error where it says, you should be compiling it to use these kinds of instructions because they're faster. Conda handles all of that and abstracts it all away. There is one catch, which is that because it's so easy to do and it works so well, so much of the time, they don't have a lot of support for when installation doesn't work. One of the interesting things there is for something where installation is harder, there are a lot of Stack Overflow questions on why didn't my installation work? Because everybody's installation works. If yours doesn't, you may not have a good idea of why. So you're very rarely going to run into some error, but that's the one drawback. Again, the problems with PyTorch, we've already gone through some of them, but
yeah. So PyTorch isn't perfect. We're well aware. So one of the big problems with PyTorch is it's a relatively new framework compared to TensorFlow, and as a result, TensorFlow has a lot more ops that were just built in over time. Like if you want to do certain distributions, sample from certain distributions, certain complex operations or others, or some niche operations that you might only use in specific settings. Odds are TensorFlow will have built those up over a while. And PyTorch is closing the gap, but there still is a gap, unfortunately. So PyTorch doesn't quite have everything. Let's see. Another is that TensorBoard isn't officially supported. There are sketchy GitHub projects like the one we'll be showing you, but it's not natively built in like TensorFlow is.
And it's also not all that sketchy. It's on pip. It's well documented. There are a lot of people using it. The TensorBoard that we'll be using is just fine for your purposes.
Mm-hmm. And again, as we've gone over before, like due to the define and run nature, or defined by run nature of PyTorch, it is going to be slower in some cases because we can't build a static computation graph like in TensorFlow. So often on say mobile devices or other things like that, TensorFlow has a lot more support for that reason. I'm sure that PyTorch will, like many things, close that gap, but for right now, the reality is what it is. So
this is the bottom line, which is if you're doing research or researchy things where you care less about, I have this extremely well documented model that someone else built for me and I want to run it quickly, but rather you're building something and you want to say, oh, I wonder what happens when you add this regularization term, or I wonder what this weight looks like over time, or anything like that. It's always going to be faster to write with PyTorch. One of the things is that PyTorch may be, even in the worst case, twice as slow, but it's twice as fast to write, and it takes you a lot longer to write these things than it does to run them, because you can run them overnight. So this is what we're saying about PyTorch, is that if you're doing something researchy, it's a good idea, and in the future it will be an even better idea, and it'll also be a good idea for production type environments, perhaps. The other thing is that with ONNX, which we'll be showing you, there is a significant push to make these frameworks compatible. Define a model in one, run it in another, and PyTorch is very much on that bandwagon. So we're going to go into the demos, and again we have to escape and pull up the notebook.
Yeah.
Any questions?
Question. I think you mentioned that you don't have to write C code in PyTorch. Where do you have to write C code?
So you might have to do it if you're defining low-level things that don't quite work as well. So like Nate was saying, where what we were talking about with building your own loss functions or doing weird things with the optimizers, because those are abstracted and separated away in PyTorch with nice modularity, you don't have to do that. But as we saw with the TensorFlow example, they're a lot more intertwined and built in with each other, so you can't as neatly separate them in Python. Does that make sense? Alright, so let's pull up the TensorBoard one first.
These demos are not going to be ones that are a lot of live coding or anything like that.
Yeah, simply, for one thing, in the interest of time, and also because just explaining them is not quite as necessary. Again, if you want if you're watching this later and maybe want a refresher on how the net operations work, look back to the live coding one we did. The actual net operations aren't going to be too much fancier, so don't worry about that.
And again, for the benefit of the screen capture, we're not actually going to be writing anything in these. So just looking in them should give you exactly the idea that we have here. The first one, I believe, is TensorBoard.
Yeah. All right. We are going to go through some TensorBoard here. So
should I explain the dynamic net and then you explain the TensorBoard?
Sure.
So there are two things that we're doing here that are weird. Firstly, we're doing a dynamic net. As soon as we go down to the next cell, you'll see what we're doing. We're defining our three linear layers, but then we're doing something really weird as you go down. This is one of the examples on the PyTorch website that will show you why PyTorch is more versatile. If we go down here, you can see we run this middle one
a random number
of times. And it's not dependent upon anything else in the data. It's not some operation that you can pick.
Mm-hmm.
Every time this network runs, it'll run a different number of times.
Mm-hmm.
So this is something that you just can't do in other frameworks. In this exact form, it's not something maybe that you would need to do. This is sort of a toy example. But I suppose you could do something like this for some weird kind of regularization, something like that.
Or if you have some really weird sequences or like something like, but yeah, but still, this is cool though, and you can't do that as neatly anywhere else.
And it's a good example of how PyTorch, due to its dynamic nature, can do these things. And so if you have some weird LSTM or otherwise RNN thing in some other framework that just isn't working because it's not dynamic enough, PyTorch may well be able to solve it.
So, yeah, let's run through this. That's just the model itself. Here we have our parameters. So we have our back size, input dimension, hidden dimension, and output dimension. Nothing particularly interesting here, just noting that. And now we're going to get into the TensorBoard part of it. So we're going to have something called a summary writer, which basically is in charge of just like keeping track of all of the different things that we'll be keeping track of. So that includes the computation graph itself, the loss, and the weight distributions. So you'll see what I mean when we step through this code. So we're instantiating some data, instantiating an instance of the model, our loss function, and our optimizer. Again, fairly similar to what we have.
Before he does that, before he actually runs this, I'm going to come over here and delete the previous runs from the previous times we've run this notebook, so that we have a cleaner TensorBoard to work with.
Oh yeah, we'll explain a little bit more about why we're doing that shortly. But in the meantime, if you look down here, we have writer.addScalar. So here you can see what we're doing is we're labeling it loss, and we're going to be adding in this actual loss value when we're running our loss function. So that'll be useful once we're looking at the loss graph. That way, let's see, what else do we have here? We're adding a histogram for all the parameters so we can see their distribution. So we have like this .clone method that allows us to do that, stepping through. And then this is slightly weird in that, so we want to also add the computation graph just because it's kind of cool to look at, but we kind of have to do it in this slightly weird way where we actually have to explicitly feed in a variable to our model in order, and then export stuff using Onyx in order to actually get our graph, and then we're exporting it into an m.graph file.
So this is actually something else that you would have to install. I believe it's just pip install Onyx, but the thing that we're doing here is we want to actually see the graph structure of the network on our TensorBoard, and this is how we do that. You will need for newer versions of PyTorch, you will need Onyx in order to do that. But if you don't have Onyx and you don't want to install it right now, this will work just the same for everything except visualizing the actual graph structure. All of the weights and everything will be the same. You'll be fine.
All right, so let's run this. So now we're going to be running it for a short while. And so once that... yeah, so now right, so that's finished running. So to see the TensorBoard runs do this, so if you could pull that up real quickly. Mm-hmm. And then, so basically what happens is when we run TensorBoard this way, it'll create a runs directory which keeps track of all of like this metadata that we save, like that our writer accumulates and stuff. So it'll be in that directory. So then that's why we do that. And then let's see, once we...
So here we are. It says I did this in an off-screen console, a console on this screen instead of that one. But if we go here to, it said it was localhost at 6006.
Yeah, so
we get our TensorBoard. I believe we should have started this TensorBoard before we created, but before we ran the thing. So
we're really? That's not my experience. Usually it's like because we don't start it before then. Because if we start before we run anything, we don't have any runs.
Well, we still don't have any runs. So
Yes. I see that.
we're just gonna restart this notebook, run all the things again. Oh, I should have just done restart and run all. But we can just go through this directly, and it will do this. It has created the runs directory. We can see that. Where's my cursor? All right, so we can. Hold on a second. Oh, here we are. Okay.
Yeah,
so
there we go.
Here we have, and this is because we're zoomed in. This is going to look a little bit weird, but yeah. Let's actually zoom out. Sorry to anyone who can't see this, but at the moment, no one can see this.
But yeah, so there you can see on that screen we have our loss. You can see that it goes down much like a typical neural net model. One thing that's kind of cool here is you can play around with the smoothing a little bit. So you have the option to smooth it to make it like look nicer and see like overall trend. But if you don't smooth it, because you can understand that like when you're running it, your loss may fluctuate. So individual losses may not represent the big picture. But if you want to represent the big picture a bit more, you can do that. And if
this is all pretty standard TensorBoard stuff,
Yeah.
but we're seeing that it still works with PyTorch. Here's the graph that it created for us when we asked it to create the actual computation graph. It doesn't really have support for graphs that have a random number of nodes, because that's not what it expects. But we ran through it once, and so this is an example, and you can see it created it just fine. Except it's just not particularly interesting.
Yeah. So
it's a simple.
Yeah. Hold on. I'll say something, then I'll answer your question. So that's actually why earlier, in order to create the graph, we had to run through the model once. It's actually because of, I guess, things like this, where it's like because the model isn't the same, it has to get a sense of what it is at runtime. So we have to run through the model once with an example, and then we can create the graph. So yeah, what's your question?
So far, like I was running the graphs are not shown, but scalars are working, so I was thinking.
Did you install Onyx and everything like that? Do you have Onyx? Did it throw an error at the end of your running of that notebook?
No error.
So previously, earlier today, I hadn't installed Onyx, and it wouldn't create this graph. But that's because it was throwing an error that it couldn't even save the graph because I didn't have Onyx and I wanted to do it with Onyx. So that may be what happened. All of the other writer things worked fine. We can see if we go to distributions, it'll show us the weight distributions over time, and the biases. If we go to histograms, same thing. All of these are rather less interesting.
And yeah, you can also see, I guess, like the bias again. Like this isn't particularly interesting right now. Could be useful if you're doing like some weight analysis or something, or if maybe you have some weights going to like infinity, or like something's not going right. This could be useful to debug, much like the loss. But this is just to show you that you can do what like used to be one of the great perks of TensorFlow is TensorBoard. So now you don't need TensorFlow anymore. But I mean, you technically still need it to run it, but you don't need to actually use it. Hopefully someday you won't even need that.
So we can see that this whole TensorBoard thing works just fine. And what we can do is we can restart the kernel and run it all again. And it'll create a new run, just as we expect it to do in any kind of situation where you're using TensorBoard. If we go back to the TensorBoard tab.
Does anyone have any questions about this demo? Yeah?
How did you launch TensorBoard and stuff?
So basically, what we did was we had so there's a command. If you go to the bottom, you can do this command, TensorBoard --logdir runs. Because, again, as we said, the runs directory will be created there, and when you have it installed, you can do that, and it'll launch it from that appropriate directory. Any other questions? All right. You want to move on to another demo now?
Yeah, let's move on to the next demo. I believe the next one, I'm going to close out TensorBoard and also the TensorBoard demo notebook. I believe it saved it by now, yeah. All right. So we just saw dynamic net. This is the same thing except without the TensorBoard, so we don't need to do that. The next one, we could do SciPy or nearest neighbor.
Yeah. Do you have any preferences to?
This one says nearest neighbor, whichever one.
All right. Sure, we can do that.
All right. This is a project that I did basically just to teach myself PyTorch, but it's sort of an interesting perspective. And this is bad code, but it's sort of an interesting perspective on how the types of code that you write will always make sense in PyTorch, even if you're doing something really weird. So the idea of this was taken from Chris Olah's blog, and the basic idea is if you have a normal neural network, at the end of it you're doing linear separation of the classes, because that's what the linear and then the softmax is. You're classifying them with these linear boundaries. That may not be what we want. Maybe we want something that just puts the same ones near each other. And so we developed this idea of the nearest neighbor layer neural network. What we have here is a similar sort of thing, but what it enforces instead of linear separability is good clusters. So if we start running through this, we can see we do all the normal things. We're defining this module called distance invert, which basically just takes the inverted distance between two tensors, or variables, because it is a module. We're going to do all this early processing of the thing. We're going to load our model like or load our data rather like normal, and we can see that we're working with the normal. We can visualize our data. It's the normal MNIST type stuff. And then we have these things. Basically, the way we're going to enforce good clusters is we're going to use this dist invert thing with a softmax on top of it, and we're going to basically have the inverted distance of the last hidden state between whatever it is we're running through the network and these nice examples of each of the digits. I'll show you what I mean. So we think that this is a nice looking 0. So we think that once we're almost done with the network and we're about to do the classification, all of the ones that are 0 should have been mapped to somewhere in that hidden space that's close to where this one was mapped. Same thing with the one below it. All of the 1s should map to something similar to this. All of the 2s should map to something similar to this. And you can imagine that not all of the 2s are actually similar to this here, right? Maybe it's shifted, maybe there's a loop in the 2, and so the actual difference between the input vectors is large. But what we want is that after it's been run through the network, the distance between this second to last hidden state, the last hidden state before the classification, they should be similar. So we have all these, sort of platonic ideals of these images. And if we go down to the next one, we're going to build the feature extractor, and then we're going to use that feature extractor and just compute the inverted distance between the one that we're running through, x, whatever our input is, and each of the platonic images. We're going to take the inverted distance, and that's how we're going to do our classification. So we can see this is what PyTorch tells us we have. We have this. You can see I used the sequential class, and it was really easy. There was no huge amounts of code. We have our conv ReLU pools things. We have our 2 linear layers. And then we have our distance inverting. Because distance invert doesn't have any parameters, we didn't really need to write it in a module subclass. We did anyway. It shows up, but it doesn't have anything inside it. So then what we do is we look here, and we have we will basically just turn everything into variables as necessary, make sure everything's working fine, and then we could run this. We're not actually going to do so because this one actually does take a little bit longer to run because you have to run 10 more images than you expect at every batch. But we're going to just load in a pre-trained model for this. This is in the repo as well. So let's see. This is just a warning, isn't it?
Yeah, no, like I was running it today and it's fine.
Okay.
So yeah, don't worry about that warning. It'll work.
So let's just take a look at the accuracy. This may take a couple moments.
Mm-hmm.
And then we will look at one of the examples and what the distances or the inverted distances are between it and all of the actual Platonic images. Any questions about this? I know I went through it pretty quickly.
How do we choose these Platonic images?
I literally just went through them, just randomly selected images from the MNIST data set, and whenever I hit a good-looking one, I was like, that looks good, and I saved that one.
So
there's no trick to it.
So yeah, we can see there we have accuracy on the test images 0.9553.
Again, that's not particularly good. 95% accuracy isn't particularly good for MNIST, but this is sort of experimental, and it's actually requiring something rather stronger than linear separation.
Mm-hmm.
I don't have it in here, but I once did random projections on this, and you can see that it really does do some very nice clusters. So we can see this one is a 7, and if we look at what it's closest to, if we have these things here, the one that it's closest to, that is the one where the inverted distance is the highest, is the 7th one, 7, 8, 9. So the 7th one has by far the lowest distance, and so the highest inverted distance, and that's why that got mapped closest to 1 after the softmax.
Why do we take a inverted distance?
Inverted distance because what we're doing is we're trying to maximize that value.
Okay. Why don't we just minimize it?
We could minimize the distance. Well, I wanted to put a softmax on top of this, which works well for maximizing a thing rather than minimizing a thing. You could just as easily do it with minimizing distance instead of maximizing.
Yeah, I guess you could just negate the softmax or whatever. But yeah, I guess just the way it's written,
All right. Any questions about this demo? If not, we're going to go on to the final one, which is pretty short, and it's just showing that you can use SciPy's convolutional operator.
Mm-hmm.
All right, I believe this is yours.
Yeah, could you just pull that up quickly?
Yeah, it's in here. Whoops. If we go back, SciPy.
Yeah, so again, the goal here is to just show that we can use custom operations pretty easily. So we'll go through our usual imports, and here you can see from SciPy.signal we're importing a convolve and a correlate function. Both used to do like pretty similar things. So here you can see. So in we have a SciPy conv2D function, and that one we're not inheriting from the module class. We're inheriting from the function class, which is slightly different. And as you'll see shortly, here we actually do have to write our own backward for this. Because we aren't taking a native function, we actually have to write it out. So as you can see here, so first we're just doing our result, which is so our input and filter are tensors, PyTorch tensors, because that's what required. But they have a numpy function we can use, as you can see over here. And we're doing it with valid mode, and then you have this save for backward thing, which is because of how we do convolutions and how the gradients work, we need the input and the filter when calculating our gradients. So we actually have to literally save them so that we can use them for calculating those gradients. So saving them, and then we're returning a float tensor because you have this nice method of casting as your result. And now if you look in the backward here, we actually have an attribute self.save tensors, so we can load up our input and filter much like how we save them in. And then what we're doing is we can and we have this grad output, which basically, if you remember again how the gradient and creator worked in our variables, is just a way of saying, okay, this is the gradient, coming in that results from the output of this variable we're looking at. So, standard chain rule applying here to calculate that, so we need the gradient output. So anyway, we're convolving the gradient output with our filter, and then for the filter, we're doing the same thing with the input. And then, because we have an input and a filter, we have two separate gradients for both of those. So we return both of those as torch float tensors. And then we actually have this module here, which we can build on top of the function we defined. So here we can just say, okay, our filter, we're going to make a parameter class, much like we had before. And then for the forward, we can just return the function output on our input and filter. And, again, we don't need to write a backward for this because we wrote it for the function itself. So here you can just see we're calling it with an example, and we're actually calculating some backward stuff manually. And it works. Does anyone have any questions about anything I did? Hopefully this one, since it's shorter, it makes some more sense. Yeah?
Oh, I just got an error that says name variable is not defined.
Oh.
They updated the repo.
Yeah.
Slide it imports, just import variable.
Yeah.
Can I see that cell again?
Sure. All you have to do, if name variable is not defined, the only thing you have to do is just add up
From
here.
torch.autograd import variable.
Is that updated in the repo that I pushed? My bad. Sorry, I forgot to push that one. That's the only line that's different.
I also I think you also need to update the one for the TensorBoard, because I could not get that one working either.
Really?
Oh, what about it couldn't you get working? One of the things that we forgot to mention was that you needed to install Onyx. And so that wouldn't have done the graph. And there's also some quirks about you need to start running TensorBoard first, and then run the code in the notebook. In any case, did other people get TensorBoard to work? So maybe and maybe not. In any case, if you didn't, just come and talk to us afterwards, which is basically now.
Yeah.
And we'll help you get that working if you want to see how that works.
Mm-hmm.
So in this network, we're just defining the forward to be a correlation.
Yeah.
And then why is the backward then a convolution?
Oh, because when we're because that's what happens, when you're doing a convolution for your forward, then the backward is actually also a convolution, but applied differently. So yeah.
Anyway, this is the end of all our demos and everything. So that's the end of the workshop. Again, if you haven't filled this out, this is the attendance and feedback form. Mm-hmm. And then, come up and talk to us if you have questions. Any other questions that are going to be of general relevance?
Well, if not, we thank you for coming out, and we hope you enjoyed it.